Now I guess people can see my screen with the GitHub page, right?
Yeah, you can see it.
Okay, so if you are in the GitHub page, you just click on this Open in Collab button here, and it will open for you in Google Colab, if you have an account in Google, of course. And yeah, so I prepared this tutorial mostly to demonstrate what you can do with ULaMDyn. The pipeline I was talking about before. So the philosophy behind ULaMDyn is to have two different ways of running the code. You can either run directly in your terminal and get all the analysis done in a single shot, or you can import the package to your Python environment and have more flexibility to do your analysis. So yeah, so let's start. So you just need to run the first cell that is going to install, and you take the ULaMDyn from our GitLab repository and install some of the dependencies like the py2dmol for visualization. And I also have prepared some trajectory data. It's not the full data set that I used in my talk, but it's just some trajectories that I selected for the tutorial. It's also available in my GitHub. But if you just run this, it will take the whole data set, the TGZ file. So it's, if you look at this, yeah, so you have already the ULaMDyn package installed in Google Colab, and you can also see this nx trages fulvin directory. And inside of this directory, we have the many trajectories that I was talking before that was generated by NewtonX. And inside of each one of these trajectories, you have the results folder with the text files with all quantities that were calculated during the dynamics. Basically, what ULaMDyn is going to do is to check all these trajectories folder and take the information from these results directory. So yeah, there is one detail that I put here. I don't know why, but there is some problem of import if you don't restart your runtime. So please, when you are going to run, before importing ULaMDyn here in the other cells, you should just click in the runtime and restart runtime. You should do this, because otherwise you get an error. I put an warning here on top. So then, yeah, so we should ULaMDyn work if you are inside of the directory that has this traj folder. So we need.
Max, I may interrupt you. Josene and I are having problem to get the Incolab. So what could you help us to get there? Because we went in this link that Pablo gave on the chat.
I didn't see the link in the chat. Let me see. You can see my GitHub page.
Yes.
And you click it on the Google Colab button.
No. No, sorry. Which GitHub page?
Let me just try to share 1 minute. Where is the chat? I can see the chat. Ah, chat. Okay. Yeah, this one that Pavlo put in the is this one.
Okay, so if I go there,
there is a button.
Down.
Let me quickly show here. Can you still? Oops. Okay. Because there is a. Can you see the screen with the dark page?
Yes.
Do you see this button here, Open in Colab? Below the ULaMDyn tutorial. that is
Yes.
written. So you just click on this open in collab and should go to the collab page. But you should be connected to, probably you should be using, I don't know, Chrome. I always use Chrome. I don't know about other.
Yeah, for me, no, it's fine. And also for Josene.
Okay,
Yes, this one worked well. Thank you.
okay.
What should you
So-
do now?
Now you just need to run the cell that is kind of gray. The first one is written bash. It's a % bash. When you run this, it's going to install your the ULaMDyn package in your system in Collab. And after that, you have another cell which is also a bash command to get the data set from the GitHub page, right? And then you have a tar command to unpack this and remove the old one because of space. So the space may be also a problem because it is this data set should have a few megabytes of.
I have a question, Max.
Yeah.
If you open these trajectory folders, right, there are many files, right?
Yes.
So these results, so it should
Yes.
be in this format, right? Otherwise, it will not work, right?
Sorry, say again.
It should be in this format, like dyn.out, like the format.
Yes.
Otherwise, it will not work, right?
Yes, exactly. Yeah.
So it means you need to use Newton-X.
At the moment, yes.
Right?
Yes, at the moment, yes. If at least if you want to run in the terminal, for instance, it's interfaced only with Newton-X. In the future, I am planning to make other interfaces, but now it's working with Newton-X, both with the classical version, that is this one I am showing here, and the new version. In the new version, we have all the information in the AGF5 file. So ULaMDyn will recognize that there is this AGF5 file and we will read the information from there.
I see. Thanks.
Okay. So yeah, for those that maybe lose the other steps. So after running these two first cells, you need to run this one here to make sure that you are inside the trajectory folder. So when you run this cell, you see that the program already can see the trash folder that we have, right? So the only thing we have is the trash that we generated by Newton-X and this geom.xyz file that is a reference geometry to calculate some descriptor, for instance, or the RMSD. And this one is the geometry of the ground state. So ULaMDyn will check for this file. So you should make it available inside your folder. Okay, so yeah, I was talking before that we have two possible ways of running ULaMDyn. One is via the command line interface. In Google Colab, every time you put this exclamation marker in front of the command, it means that it's going to run like a Linux command in your terminal. So if you run this, you get the help information that is the same that you see basically in the bash script. And to be able to run the full workflow, it's very easy. You just put the run ULaMDyn, that is the interface script to manage all the steps. You define the task, in this case clustering. You define what is the space that you want to consider, which means if you want to group your data set by geometries or by trajectories. If you put dash space equal to geoms, you have every data point as a molecular geometry, and the algorithm will try to group them, taking from different trajectories. So here you define how many samples you want to take from these trajectories. Just for demonstration, I'm taking 500. The descriptor that will convert the XYZ geometry into this vector representation. In this case, is the RE. That we will use the equilibrium geometry that I talked before. Finally, you can put the method, k-means, and the number of clusters. So if you run this command, so ULaMDyn will start to perform the analysis by reading all the information. So you have still some output saying that is going to take all the information available there. It takes some minutes to run. Mario, everything is fine from your side?
Yes.
Okay. So yeah, so now the algorithm is just collecting the information. Now it's doing the k-means analysis. You have this information of what are the hyperparameters used for the model, and finally, when it does the grouping, it will output the geometries that were found assigned to cluster 0 and cluster 1. So we have 400 geometries to cluster 0, 98 geometries to cluster 1, for example.
A question, Max. These hyperparameters, they are predefined or they are found for this specific set. Can you redefine the hyperparameters? Do you have a control on that?
Most of them I define it based on my tests. So if you are running in the line command, like we are doing now, it's a bit hard to define everything. Some of them you can change, like the number of clusters, for instance, but some other not. But if you are running in the Python environment, you have the flexibility to change basically everything.
Thank you.
And statistics for you. So for example, it will take the property data set that contains energies, a lot of quantum chemical properties calculated for the trajectories, and calculate the average and the standard deviation of those things. If you go to the folder, you can go to this NEX trajes folder, and at the end you see a lot of files. Let me just you have these CSV files that contains the statistics for your analysis based on the cluster. So you can just open these files and you will see the statistic information there. You have also a CSV file that contains the labels for the 500 points that we selected. And we have also some XYZ files that contain the geometries attached to cluster 1 and the geometries assigned to cluster 2. So this can be, you can just open these using VMD or Gmol or whatever. And the one that corresponds to the centroid of this cluster, so the center of the cluster. In the case of k-means, it makes sense to have this because it's based on a centroid approach. So I will just clean the directory before we move on, so to have everything fresh. So I will remove these guys.
Sorry, can I ask a question about?
Yes, of course.
About these number of clusters, like you mentioned that give me 2 clusters, right? But maybe there may be 3 clusters or 4 clusters. So how to optimize this number? Like people usually like in these and medical side, they also do this unsupervised learning about these cancer cells, and when they do it, they don't define number of clusters. The algorithm itself just clusterizes the cells, and it shows, okay, 13 clusters or 10 clusters. Like they don't mention number of clusters. So
yeah, that's a very good question. There are some algorithms that allow you to give this parameter free, and the algorithm will find this for you. For example, hierarchical clustering can do this. You just need to define, instead of defining the number of cluster, in the hierarchy, you need to define some cutoff distance to say, okay, this is the maximum distance that I'm going to merge points to form clusters. That's a different parameter. And, yeah, you have some cutoff to define where the algorithm should stop. In the case of k-means, you need to provide this information afterwards. But you have some metrics that can be used to find the best number of clusters, or the ideal number of clusters. And most of these metrics are based on two concepts. One is how compact the clusters are, because you want your data points to be as compact as possible, and how separated these clusters are. So points that belong to the same cluster should be very close to each other, and points that are assigned to different clusters should be very far apart. So these two notions is that people use to define metrics of what is a good clustering. It's only based on how your data is distributed. So in the case of ULaMDyn, I implemented an option for k-means that you can put like here best, and it will use two different metrics of clustering to find what is the best number of clusters. But you should use this with some care, because should be careful with this approach, because not necessarily the number of clusters based on these two concepts of compactness or separation between clusters is the best way for your data set. You may have, and if actually Fulvin is a very good example of this, because I shown before that you have two different types of geometries for hoppings, and they overlap. So if I not use k equal 3, I cannot see these three groups. Probably if I use just a metric based on the separation, the algorithm is say to me that I should use k equal 2, because there are two overlap groups.
I see.
But it makes sense from the point of view of chemistry to have three groups, because I have two types of hopping geometries.
Mm-hmm. So it depends, like it's all analysis. You need to analyze your data and then see what's the best.
Yeah.
I see.
But yeah, we have this option to use the best here, and it's one way if you can just get started and see what's going on. But then it's important to make this other analysis of plotting the histogram, see if it makes sense from the point of view of chemistry of your data set. Okay, so now if you have run these two cells, it's just to demonstrate that you can do this in the command line interface. But now it's the most interesting part. You can just run these cells. It's some imports. I'm going to import ULaMDyn as UMD, some other dependencies for the next test, define some plotty settings here, which are not very important, and the one function to visualize the molecules in the Jupyter notebook. So how the workflow starts? So of course we need to get the data first. So we have a function, for instance, to collect all the geometries. This is done in a modular form. So we have this class called getCoords that take care of only reading the geometries from Newton X trajectories. And when you do this, it's going to read all the geometries. And after that, if you print this, you see that this object recognize all the trajectories that were available in the folder. Also the atom labels that is used to compute, for instance, mass weighted coordinates when it's required. And this is the total number of geometry that was loaded from all these trajectories. And here we have a nice thing. This object, you can easily select the geometry of a given trajectory in time. You just need to pass two numbers. The first number is the number of the trajectory, 9, and 10.0 is the time step that we are going to read. So if you do this, you have the XYZ of trajectory 9 at time 10. And you can use this XYZ format to quickly visualize and see. Hopefully it's going to appear yeah. So then you can quickly look at your data. If you just put one number, an integer like I don't know, 100, it's going to take the geometry that is in the order of your data set. So if you put 100, it corresponds to trajectory 1 times step 10. If you put, because it's in the order of trajectories in time. So if you put 200, the same. So you have these two options to analyze your data set. You can look at the geometry and see what's going on. And why I did this, I fully recommend if you are doing this kind of analysis to take a look at your data before doing anything. Because it's important to know if you have, I don't know, maybe outliers. This is something that's not implemented in ULaMDyn. If you have some hydrogen that is going away and maybe is going to contaminate your clustering analysis and so on. So it's important to quickly check if everything is fine with the data set. We also compute by default if the geom.xyz file is available, the reference geometry is available. We compute the RMSD between every frame of the trajectories and these reference geometries. So this is the distribution of the RMSD. So we have some very distorted geometries with this long tail here, but most of them are around 0.2 angstrom of deformation compared to the ground state. And then we have some other functions that follow the same principles to get information of properties. We will check a different file of NewtonX, but it's the same idea. So you just run this to get the energy, for instance. And here you have this properties data set. And in the properties data set, you have one column with the trajectory and another one with the time. And these two indices should be unique. So they define any specific point in your data set. So they should be consistent across different data sets. For the molecules, for the geometry should be the same. 1 and 0 should correspond to 1 and 0 here. So then you can just concatenate them to get a complete data set. But then you have the total energy, the energy of the ground state, energy gap between every state that you have. If you have more states, ULaMDyn will calculate all the energy gaps between them. And these columns that identify the hopping geometry. So if it's 0, it's not a hopping geometry. If it is 1, it's a hopping. So you can easily go to the data set and select the hopping geometries. And then you can extend this selecting like populations, that is a standard quantity calculated in this type of simulation. And after you run this, you can update
Max,
your data. Oh, yeah.
you are too fast.
Oh,
should
sorry. Sorry.
Just give us a second to catch on.
Yeah. So are you in the same stage or are you running the same cell or?
Yes.
Yeah, basically everyone can interrupt and basically stop and ask questions and say, okay,
Yeah,
it's just too
please.
fast for you. Yeah.
Yeah, please do it because yes.
Oh yes, I'm doing.
So yeah, so far, let me just do a quick recap. So we are just in collecting the information to make the analysis. And this is stored in different data sets. So we have a data set only with the chemical properties and another one that was loaded before here that contains information of the geometries. And both are important because For instance, if you want to plot the histogram of the energy gap for the clusters, you need this data set with the properties. And if you want to run your clustering algorithm on the geometries, you of course will need to run this loaded geometry first. But this is the main two steps. So after running just a quick demonstration of things that you can do for this type of data set, you can, for instance, create an histogram of the energy gap for the hopping geometries and for the non-hopping geometries. That is what we do, I think. Let me see if oh, it's not this example yet. Oh, yes. Let me see. No, this is the histogram of the energy gap across the full data set, right? So you can split this histogram by selecting the geometries. Let me just create one cell more. For example, df props dot query. Let's say you want to look at the hoppings between state 2 and 1. So if you want to check this, you just select the hops as to 1 equal to 1, and this will list to me all the hopping geometries. And you have the time that this happens and so on. It's as simple as this. Dot query, and you put your name of the column, equal to 1, and you select all the hopping geometries that you want to analyze. So yeah, so now we already have our data set. We have a data set for the geometries, and we have a data set with the chemical properties. We can move on to the next step, that is the descriptor. So remember that before I have run this geoms loader, that is a Python object, and as a Python object you can access the attributes of this object with this dot, right? So in the dot xyz that contain all the geometries that were collected from NewtonX outputs. All right. Yeah. Then you see that you have an array of dimension any samples, any atoms, and tree. So that is the structure of our data set, right? So now what we can do, we can calculate the R2 descriptor, which is essentially the pairwise distance between all atoms in the data set. For that, we can create this object. So ULaMDyn, the package, R2 is the class, and I give as input to this object the geoms loader that I shown before. And this this class R2, it contains a function, a method called build descriptor, where you calculate all the pairwise distance if you put the R2. If you want to calculate if you want to get as output the inverse R2, you just put like this. If you want to get the RE descriptor, you just replace by RE. Right? And then let's just run this cell. So it's calculating the pairwise distance for 30,000 geometries. So it's a bit, but then you get a data set. Again, you have the two indices, charge and time, to identify every point in your data set, and a vector of pairwise distance So, for example, one that is not shown here because of these three dots is the R56. That is the two important atoms in fulvene. And just to give you an example of what you can do with this data set, you can select all the geometries that belongs to a hopping and the geometry that is not a hopping. So if you do this and filter your data set in this way, that is these two commands here, you can plot the distribution of the C5, C6 bond distance that comes from this data set for the hopping geometries and for no hopping geometries. And we see that the red bars that correspond to the hopping geometries, they are shifted to large C5, C6 bond distance. Because as I said in the talk, at the very beginning of the dynamics, we have this bond stretch of the fulvene that brings the system most of the time to the conical intersection. So if you plot the two distribution, you see the difference between them. So the hopping geometry are most concentrated around 1.55 angstrom. So yeah, just to take a look at your data set and see what's happening with the data set. Another way of looking at this coordinate, you can plot your bond distance as a function of time. So your x-axis is the time, and the y-axis is the bond distance. And I can add some information about the hopping geometries. It's another way of looking at this information, and you see that there is an oscillation. So there is a bond stretching at the beginning, and then it contracts and they stretch again. And most of the hopping points, that is the red markers, appears around the maximum of this periodic function. So yeah, up to this point, everything we did, it was just an exploration of the data set to see what are the features important for the data set. You can play around with this. For some tests, you can even stop at this level if it's enough for you. It depends on your problem. But here we can move on to the dimensionality reduction, because now, let me just quickly show you. If we look at this DF-R2 data set that contains, show you again, that contains all the atom distances, we see that we have 68 columns, -2, because the trajet time, we are not going to put this into the descriptor, so it should be 66, right? Columns. So the length of my descriptor is 66 components. Every geometry in the dataset is described by this vector. So we can, of course, we cannot visualize this, but we can use dimensional reduction to reduce these 66 columns to 2. And in ULaMDyn, we can do that by using this dimension reduction class, where you pass as input the dataset. And this dataset is basically our descriptor. We can also slice the dataset by a large time step. Here I'm considering 0.5 just to get less correlation, because the geometry at time 0 and 0.1 are very similar. So this makes the algorithm much more difficult for the algorithm to find the pattern, because you have a lot of correlation. So one way of removing this is to use this DT that is going to take the data set at every 0.5 time step instead of 0.1. And here is the scalar, which means that every column in this data set will be mean centered. So you just shift by the mean and make the standard deviation equal to 1. So you have your column and you subtract from the mean of that column and divide by standard deviation. That's which means this is standard here. This is done once you instantiate the model in red. So it's saying here that you will scaling your data with this standard method. And now we have this object called DIMRed that can give you access to many different, well, I think it's four. A question?
No.
Yeah, so with this object called DIMRed, you can access the method you want to use for dimensionality reduction. Here, for example, I'm using the isomap. That is the nonlinear method for dimensionality reduction, the isometric feature mapping. I put here some explanation about how the algorithm works. So if some of you want to get more details, there is also a link for the original paper of isomap that was published in Science. And basically here, when you do this dot isomap, you can give any components equal to 2, meaning that your original data set will be compressed to two columns only. So you have an original data set that contains 66 variables. It will compress these to 2 dimensions. And if you put a comma here, you can add more details about isomap. For example, you can define what is the metric that you are going to use to compare 2 data points. Can be Euclidean distance, can be a cosine distance, and so on. So yeah, I think it's just metric equal to cosine. If you want to change the metric to use. So the default, I think it's cosine, but it will be printed anyway. Yeah, so the default is cosine. So here you have this number of neighbors is related to how you build a graph around your data points. So it will consider 30 neighbors to build the graph that is used in this method for dimensionality reduction. And you have also other parameters like the number of dimensions. This is the most important one because you want to visualize your data. So you just select number of components equal to 2. And this now processing. It takes some time because isomap is a bit expensive. Yeah, so it runs. So now if you look at the data set that was generated, isomap, DF isomap, you have 2 columns, x1 and x2, that represents the original vector in a compressed form. So we can now plot these in a scatter plot that we do right here. So we have this plt.scatter to plot the 2 components, x1 and x2, and we color the points according to the energy gap between the 2 states that it comes from this DF props dataset. So now you can see why it's important that everything is matching, because these 2 datasets, the DF isomap and DF props, are different, but they share the same indices. So then we can use this information to make the plot. So if you run the cell, you get this. That's more or less similar to what I shown in the talk. It's a bit different because I have less points than I use it to generate the picture for my talk. But the idea is more or less the same. So you have some kind of circular distribution of points. And also you can see that there are a lot of points very, very close to each other. And that's because even with the 0.5 time step size, we can see that there are a lot of correlation between the points. So they are not very different. So this sequence of points is probably from the same trajectory. But the most important thing here is that we can, again, we can see that points similar to each other are more or less in the same region, that blue points that correspond to the low energy gap, the small energy gap, and they are not mixed with the red points that corresponds to large energy gap, or even intermediate values. They appear in a different region of this diagram. So this makes very easy to select what is the important molecules in your data set. Then you could ask, okay, but I could just select the molecule based on some property like the energy gap in this case. Yes, but you don't know what is the threshold that you should use to make this selection, right? And in some cases, you have geometries that are assigned to that correspond to a small energy gap, but they looks different somehow. And this kind of diagram allows you to check what are the difference in each region of your data set. And yeah, so far so good, but we as I said, that we compressed the whole information in only 2 coordinates. So now, because this method is nonlinear, we don't have any more information of what x1 means, because it's not a linear combination. Like in PCA, x1 is a linear combination of your features. So then it's easy to interpret, because you take the feature with the largest weight in this expansion, in this linear combination, then you know what is the feature that is contributing the most for your dimensional reduction. In the case of isomap, you don't have this because it's a nonlinear method. But what we can do is to plot the x1 as a function of some of the features. For example, in the case of fulvin, we expect that the distance between atom 5 and 6, that is the bond stretch I talked many times, is one important coordinate. So if it is an important coordinate, it should be somehow reflected in these x1 and x2. So we can do a linear, a scatter plot of these 2 components, the x1 that comes from the isomap, and the bond distance that is our feature. If we do this, we see that there is some correlation. So the x1 is really capturing some information related to this bond stretching, to this bond distance. And you can do this for many other features, like probably you have distance between atom 1 and 2.
Sorry, Max, may I ask a question?
Yes, of course.
So basically you don't have an analytical expression for they are not principal component, but for x1, x2 using the isomap.
No.
Okay, I see. So the point in the isomap is to represent basically a topology in the smaller spaces possible, but there is no meaning of what x1, x2 mean for each point, because it may change.
There is some meaning, but it's not just, at least as far as I know, there is not an analytical expression, as you said, to get back yeah, to
the coordinates.
Yes, yes.
Oh,
You don't
see.
have this relation. But for example, in the case of the TSNE, that is stochastic, then you really lose the meaning. You just observe some groups, but because the method is stochastic by definition, you really lose the information of this coordinate. So it does not care any. If you do this kind of plot, you probably not see any correlation.
I see.
But this is for TSNE. In the case of isomap, you can see that it is encoded in the X1. You just don't know the expression. But yes.
I may take the chance to ask you a follow-up question that is actually not super related with this section, but it was something that I was actually interested in, and is more related with the concept that Todd Martinez introduced for the photochemical reactor. So how basically you can partition the space around minimal conical intersection and understand the different products that they form. And I don't know with FullVin, I guess it's not really practical, but you try to using like clustering methods similar of what you're doing for non-adiabatic dynamics here, but for instance, reproducing their result with benzene. I don't know if you ever try. It was just
not yet, but it would be a very good test. I saw a talk related to this, and I was looking for some other data sets. There is, I think it's the cyclohexadiene. There is also another data set that I was trying to get for this tutorial, because after the dynamics, you have many possible products. Some of them, the ring is just broken in 2 parts or something like that. I think it's the same thing they see in benzene. So you have many different types of products. This is very interesting for the other part of ULaMDyn, that is how to group the trajectories by similarity, which is very challenging. We also
not
have
with
a function
geometry,
for that.
but
Yes.
Not for each geometry, but partitioning the different trajectories.
Yeah, if I come back, for instance, to this plot, you see that all the trajectories are kind of very similar, but if the geometry end up with a different product, you probably have lines going to all the direction.
I see.
But this is happening with the many degrees of freedom that you cannot see in a single plot. So there is a technique for this to group trajectories by similarity, the multivariate time series. We implemented a function for this, and I'm trying to have some data set that I can test this, because in the case of FullVin, it's probably not going to give anything.
And I actually, now that you mentioned the trajectory, I have actually another question. Here you did with FullVin with CASCF, I guess, or some some multi-reference method. What's about instead if you're using single reference and maybe you have to switch manually to hop on ground state or doing some kind of funky stuff? Like, I don't know, if you use a DC2 or TDFT, there is a way to switch manually on the ground state, but the collection of the data will be exactly the same as here? I don't know how to deal with that.
That's a good question. I don't have a good answer for that. My feeling is that the data set would look different, especially if I intentionally make the hoppings to occur in a totally different region, like in the minimum of this curve.
Yeah.
So, yeah, my intuition is that this is going to be very different, but I cannot tell you how it would change. But it would be interesting test. Yeah, thanks.
I mean, usually you want to up like when you have very close in energy. So if there is a correlation in energy gap and C5, C6 distance, I guess you would not look that much different in this case. But I don't know how to deal with other cases, but it was just a consideration that I don't have an answer for that. So I don't know.
Yeah.
Thank you anyway.
Okay, thank you. So, yeah, so just coming back to this plot, yeah, so you can do several different plots like this one to try to identify what is the most the highest correlation between the features that you have and the X1. This is one idea that I saw actually also in the paper of Professor Zhang. They used something similar to this to identify, in the case of nonlinear methods like isomap, what is the information encoded in these compressed dimensions like X1 and X2. So this is let's say a post-processing exercise that you need to do to get some chemical intuition of your data set. But it was also mentioned in the discussion in the questions that why not using something different from the geometry. So in fact, we already have our data set with the full information that is very different from the kinds of supervised learning, for instance, that normally we start only with the geometries and the labels. So here we have everything. We have the gradients, energies, and so on. So the gradient is also an interesting descriptor to make this kind of analysis. I just want to quickly demonstrate this. And the idea is very similar to what I shown before. Again, you have a class in ULaMDyn to collect this information of the gradients. That in this case, will return a dictionary where every key of this dictionary corresponds to the gradients of the particular state. So you have a sequence of gradients for S1, a sequence of gradients for S2, and so on. So when you run this cell, the program is going to read all the information in the trajectories. It's done. And then one kind of descriptor that's very useful is to take the difference between the gradients in S2 and S1. Why? Because when you when the dynamics get close to the region of intersections, this difference is very sensitive to the variation around the intersection. So if you just take this difference between S1 and S2, this is going to be our new descriptor that I'm calling here the GDiff, the gradient difference. And again, you have another data set now with 38 columns only because it's depends on the size of your molecule, right? You have 12 atoms, 3 coordinates, so then 36 components, plus these 2 columns of charge and time. And basically, we can do the same thing as I did before. So I create a new dim red object where I put the descriptor, where I give this descriptor JDiff as input. I am going to slice them again by 0.5 and standardize the data. After that, I can apply the isomap algorithm as I did before, but now I'm using the Euclidean distance because my data set is more compressed already, 38 columns. It's better to use Euclidean distance in this case. So you can run this. Mario, is everything okay from your side? Are you still there?
Yeah, yes.
Yes.
We changed the computer.
So, okay, so now we have the new descriptor and also we finished the dimensional reduction for this gradient difference, and we can make the plot again to see how it looks like. So I'm doing the same thing. I'm coloring the points according to the energy gap, and we see that the diagram looks different from before, as expected, because I just changed the descriptor. But now, basically, if I draw a vertical line around 0, I can select basically all the points that have a very small energy gap. So it's a very nice way of separating those points. So compared to what we had before, it's even clear the difference between the points with the very small energy gaps and the one with large energy gaps, because they appear at the extreme points of this diagram. So this is also a nice way to take a look at the data set and see what is happening with the geometries. So what we could do after this plot would be, for instance, to select all points that are in the right side from this 0 line and from the left side of the 0 line, and compare them to see how they are different. Or if you want to be more precise, you can just select the points that belong to this region where x1 is larger than 15. For example, take less points, and in the other side, take the red points around the -8, maybe, and compare them to see the difference. So that's a post-processing step if you want to check what is happening with this, why these two regions of the data set are so different.
So Max, basically you can get for every point, given the coordinates x1, x2, you can recover all information, right? So it's mapped on the database.
Yes, and that's because we have the 2 indices that match all the data sets, so we can always look for the, I don't know, from the point number 10 in this data set should correspond to the point number 10 in the other one, and then I can take the geometry that corresponds to that.
Okay, good.
Yeah. So the next part is the clustering analysis. So far, it was much more like exploration of the data set to understand the main features of the data set. But now we can just apply clustering analysis on our features without dimensionality reduction. So many times people ask me if I should do dimensionality reduction before clustering or not. This is another thing that really depends, because if you have representation that are very big or a vector that is very sparse to represent every molecule, maybe it's a good idea to reduce this, because it becomes much more difficult to compare two data points if the vector is very large. So then you can apply dimensionality reduction, not for visualization, but to remove some unnecessary or correlated components of your vector, and get something that's more compact and easy to compare between data points. In this case of full VIN, the molecule is already small, and the vectors that we use for representation are not very large, so we will use the clustering in the descriptor as it is without any dimensional reduction. So we can use dimensional reduction afterwards to see how the clustering algorithm found the different groups in your data set. So I will give you an example that will be, I guess, more clear. So yeah, so here we need to again create our descriptor. In this case, I'm going to use the Z matrix, and I need to pass as input the geoms load object that contains the geometry. So the ULaMDyn package will read all the geometries and create a descriptor for that. And here I am doing the delta descriptor, which means I'm going to take the Z matrix of the ground state and subtract or the opposite, the geometry of every frame of the dynamics minus the z matrix of the ground state. And on top of this, I'm going to apply a nonlinear function that makes the trick of taking care of points that are very different from the ground state. I want to focus on those points that are not outliers. I want to make the algorithm to find the ones that are more or less similar to the ground state. So if I run this, I can get my Z matrix descriptor. And to run the clustering algorithm that is in the next cell, I use this cluster geoms module of ULaMDyn that works pretty much the same way as in the dimensionality reduction. The idea is the same. We need to give as input the data set, that is the descriptor. We can either give some slice in time to reduce the size of the data set and remove some correlation, or we can put like any samples equal to, I don't know, 1000, and it will select 1000 geometries from the original data set. So here I will use this. And to reproduce the same results I shown in my talk, I will use number of cluster equal to 3. So once we created this object, we can just do clustering.k-means. If I want to change for another algorithm, I just need to change k-means by, I don't know, hierarchical. If I do this, it's going to run the hierarchical clustering instead of k-means. So because we store the data set at this clustering object at this level, we can run multiple algorithms and compare them very easily to the same, using the same data set as input. We just need to change the algorithm at this level, and then we can compare different algorithms for the same data set. Here we are going to use k-means. So now I'm running this. Finish it. So it found the 3 clusters that I asked here. What is here? The number of clusters equal to 3. So it will found 3 clusters, 0, 1, and 2. And one of them has just a few geometries compared to the other 2. So 500 more or less. And I already know that this cluster should contain the geometries with the rotation. And I know that because after running many analyses, inspecting the data set also, I saw that in this FUVIN data set that we have, these kind of rotated geometry are less visited during the dynamics compared to other points. So that's the reason why we have just a few geometries in this cluster compared to the other. And then also we have this data set. Let me just quickly show you. It's quite simple. It's df k-means contains, k-means contains just the labels, right? So we have for the line number 0 of the data set, the label is 2, that belongs to cluster 2. For the 5, for the row 5, we have this cluster 2 as well, and so on. So this is just the labels, and this indices here is that we use to concatenate with the other data set that we loaded before. Like, for instance, we are doing here, we are concatenating these labels with the properties data set to analyze the results. So now we have the k-means labels and the properties. So we know that, for example, this large energy gap of 3.8 belongs to cluster 2, and so on. So now it is using Python, it's very easy to manipulate this kind of data set. We have many different clusters, 3 different clusters, so we can group our points based on this. So take all the rows that correspond to cluster 2 and calculate the statistic for them, like the mean value of a given property. So I can do this in 2 lines. So for example, for cluster 0, we have in average an energy gap of 1.55. And it seems that we have a lot of hoppings in this cluster number 0, which in contrast to this other cluster number 2, we have basically no hoppings because the number here is 0. So then we can do this kind of analysis to get average information of what is contained inside of each cluster. Or if you want to plot this, you can do an histogram of the energy gap for each one of the clusters. So if you do this, you should get an histogram similar to this one, where we see that cluster 0 and 2, for instance, they are very different with respect to the energy gap. And again, this information of the energy gap was never used in our descriptor. This is a consequence of the grouping. At least from my point of view, I see as a way of checking if your clustering algorithm makes sense or not. If your result of the clustering makes sense or not. So then we have the cluster 0 and 1 that are kind of overlapping in this region of a small energy gap, which is similar to what I shown in the talk, because we have 2 different types of geometry for hoppings. One geometry that comes from a bound stretch, and another set of geometries that we have hops and are related to the rotation of the CH2 groups. So this is also possible here. Then, as I said, we can use the dimensionality reduction in our data set of differential Z matrix just to plot, just to make the scatter plot of these 2 components and color the points to see how good this clustering algorithm is for the data. So you can, in the case of k-means, I didn't mention this, but in the case of k-means, the partition, we call this a hard partition because every point should belong to a single cluster. So it's not possible to assign a kind of probability distribution for the points. There is another algorithm that can do this. In the case of k-means, every point should belong to one cluster. So the partition is rigid. If you have a data set that the borderline between 2 clusters are very close, I mean, if the 2 clusters are kind of overlapping, k-means will always draw some straight line to split them into parts. So it's common to see if your clusters are not very far apart in space, like a blob of points, you have some regions that are not very well defined in k-means because it's it can just partition in the middle. You don't know exactly if this should be 2 clusters or 1. That is what we see, for example, in this plot. So it's clear that the cluster 1 seems to be very different from the others, but eventually the cluster 0 and 2, which is the yellow and the black one, could be measured in a single cluster. So if you run a different algorithm like, I don't know, hierarchical clustering, you can end up with these guys being belonging to the same cluster. This can happen in the case of k-means. It will always split the data set into parts. well, in the number of clusters you give. So here in 3 parts. So yeah, so just approach to the end of the tutorial.
But here, sorry, but here you asked for 3 clusters, so it just gave you 3 clusters.
Yes, but what I mean is that if you, because this is already a result of dimensionality reduction, so you don't know what is happening exactly in the original space. So we hope that this picture is representative of what happens in the original space. Maybe if you add one more dimension to this diagram, like x1, x2, and x3, this group black and the white, black and the yellow would be a bit more separated. And then for k-means, it's easy to find the splitting between them. But what I was trying to say is that when you look at plots like this, for example, imagine that I don't put the colors. And if I ask you how many clusters we have here, you may guess that there are only 2 clusters, right? So if your data set with most of the time, this is not going to happen, especially in the case of dynamics, because of the points are very similar to each other in time. Because of this very high similarity between the data points, if you just plot and try to guess from the dimensional reduction how many clusters you should consider, you may end up with running with the k equal 2 instead of k equal 3. Although it makes more sense from the point of view of chemistry again to run with k equal 3. So that's usually the problem if you want to just to interpret before doing based on the dimensional reduction, for example.
Thank you.
Welcome. What I'm doing here. So yeah, so now okay, so now we have the label for the clusters, and it comes the fun part, that is to analyze and see what these labels are really capturing in terms of chemistry. We can just calculate our normal Z matrix without any difference with the ground state, just to get the bond length and angles and dihedrals. So it takes some time. And the idea is that now with the information of the bond length and dihedrals, I can check what is happening with the 2 degrees of freedom that are supposed to be the most important in FUVIN. So I can see if my clustering is really splitting the data according to these 2 degrees of freedom. Of course, in this case, I already know that they are important. In some other cases, can be much more complicated if you don't know too many things about the chemistry of your system. In this case, it's better if you just spend a bit more time exploring the data before doing the analysis to get some intuition of how the variables are distributed, or to at least to have some intuition of the results. Okay, so we have in this case, the bond length and the dihedrals, that has this D between 4 atoms. So for the C5, C6 bond distance, again, we see this difference between cluster 0 and 2 that is very significant. So the mean of these 2 distributions are quite different. And the cluster 0 is the one that contains most of the hoppings. And we have this blue one that is a bit more dispersed compared to the red one. It's kind of behind here. It's difficult to see, but this blue one probably corresponds to the 90 degrees rotation that I discussed in the talk. Okay, so now we can just create the same diagram that I shown before in the talk. So the blue clusters contain mostly geometries with a small bond length. We have these yellow ones that contains extended C5, C6 bond length. And the star markers that you see here corresponds to the hopping geometries. So the nice thing of this analysis is that we can see that some of the hopping geometries belong to the yellow cluster, that is the number 0. And some of the hopping geometries that you can see, just a few red star markers belong to cluster 1. So if you look at the geometries of cluster 1, you can see that they are the geometry with 90 degrees rotation. I can run this many times. It will just select a random geometry from cluster 1. All of them have this 90 degrees rotation. If I change to cluster 0, for instance, the geometry is more or less planar, but you have this C5, C6 bond length elongated. So we can take geometries like this. Is a bit distorted, but it's not still 90 degrees. It's probably some molecule in this region here. So this one is a bit more rotated, and so on. And cluster 2, this kind of distortion. Like most of them should be planar and with a short bond length. So yeah, this was a tutorial to demonstrate how to use.
One question. Can you do
Yes.
some advanced? Can you do some advanced analysis like Poco analysis, for instance?
Yes, we can do with ULaMDyn, but not. I don't remember all the commands now to show. But yes, it is possible to do. I guess it is like UMD.ring analysis, but I don't remember the arguments here. And here you should give some information of the geometry to do the analysis.
One thing I was reading a paper of Professor Jangang, and he was like doing this clustering, and then from each clustering, he was sampling. So this clustering can be used as a sampling method, right?
Yes, yes. There is one paper also by Kachenko's group, where they demonstrate that you can use the same training set size for supervised learning and get better models just because you have a better sampling coming from unsupervised learning, like clustering.
Yeah. So first
Because
you do clustering, then from each cluster you do the sampling. So you get like, a diverse kind of geometries.
Yeah, because you can imagine, for instance, that in this type of data set, the probability of getting points from the red region should be smaller because they are here in the data set. We have much less geometry of these 90 degrees rotation. So if they are important somehow, they should be present in the data set. So the idea is that, okay, now that you have the labels, you can say, I want to sample the same number of geometries from each one of these clusters and build the train set from this.
Yeah.
Yes.
So it was a nice tutorial. Any question?
Yeah. So it should be very late in China right now.
yeah, so I will stop recording.